Hello everyone, today's video is on 2 degree of freedom free and force vibration system. After watching this video, you'll be able to find natural frequency of 2 degree of freedom system. You'll be able to draw mode shapes of the system and find force vibration response in time domain. How to approach a vibration problem for 2 degree of freedom? It's pretty much similar like single degree of freedom. So we start with drawing free body diagram. Please remember that for free body diagram we need to draw each body separately. Then we use Newton's law equations for 2 degree freedom. That's the exception with the single degree of freedom. Then we express all kinematic quantities as a function of selected coordinate, as we did last examples for single degree of freedom. Then we obtain the equation of motion, we linearize the equation of motion, and then we solve linearized equation of motion. Keep first step which is free body diagram, as you can draw it by yourself. I'll start from second step, which is Newton's law equation. So for 2 degree of freedom, Newton's law freedom vibration system will use Newton's law equation. Why? Because for 2 degree of freedom we'll have two unknowns, let's say x1 and x2. So if we want to use work energy principle, we'll get one equation which is not enough to find two unknown values. However, for Newton's law, it will give us two equations which is enough to get two unknown values. So that's why we want to use Newton's law equation for 2 degree of freedom. There is another method that we can use, which is called advanced energy methods. However, this is out of content of this unit, so this will not be covered in this tutorial. For Newton's law, we know the equations, which is summation of F equal ma. This is for linear displacement. We can write x dot dot instead of acceleration, and we can divide into x component and y component and find the summation of x forces and y forces. In case of angular displacement, we can write summation of force equals to mass moment of inertia times angular velocity. Once you draw your free body diagram, then it will be really easy to get Newton. As we say, this is a 2 degree of freedom, so we'll have two components that will move independently. So we need to get two equations for two different mass or components. For two independent displacement, we'll have two selected coordinates. So we want to express kinematic quantities as a function of two independent coordinates. Let's try a few examples. So this is one example where we have two masses m1 and m2 attached to spring 1 and spring 2, and this is the ground, and we need to consider three cases. The first case is this one, which is a equilibrium position, so m1 and m2 don't move. So at this position, the deflection of the spring 1, we say this is a static deflection of spring 1, so we write del L1 static, and this one is del L2 static. So for first case, we write down the equation for spring 1 and spring 2. So for spring 1, del L1 static, and spring 2, del L2 static. Now we want to know what happens when each mass moves independently, and we want to see their effects on the spring deflection. So let's consider the second case, where we consider that this M2 mass stay at its position while M1 is moving at the left side with a deflection x1, and we want to know what will happen to the spring 1 and spring 2. So when M1 moves at left side, it will not have any effect on K2, so we don't write here anything because there is no effect on K2. However, for spring 1, it will extend it, so we write for spring 1 as x1 plus, because it is extended, and x1 because this is the displacement M1 had. Now our third case, where we consider that M1 stays at his position while M2 moves left side at a displacement x2. Now we want to see what's the effect on the two spring. So for spring 2, it will be extended, so we write this case for spring 2 as plus 2x2, because plus is because the spring is extended, and x2 because M2 has a displacement as x2. Now for spring 1, this will be compressed or shortened. So in the equation of spring 1, we write negative x2. Negative because it is shortened, and x2 because the displacement of mass is x2. So this is our equation of the spring spring K1 and K2, which we express as a selected coordinate, in this case x1 and x2. Let's consider another case where this is one pulley and this is second pulley with radius r. This first pulley has radius r1 and it rotates at anti-clockwise at an angle theta, and for pulley 2 it has radius r2 and it rotates at the same direction as pulley 1, but the angular deflection is theta 2. Now we want to get the deflection of K1, K2 and K3, and as we did earlier example, we want to move the masses. Here we want to move pulley 1 and pulley 2, and we want to see their effects on K1, K2 and K3. As usual, we start with the static deflection. So this is the static deflection of the springs. This is static deflection of K1, this is static deflection of K2, and this is the static deflection of K3. So we write this expression for each spring. Now let's consider our first case, where we consider that this pulley 1 is rotating at an angle theta and this pulley 2 stays still. So on this pulley 1 rotate an angle as theta 1 r1 theta. So let's consider what will effects on the springs. When this moves, K2 will be shortened or compressed. So for K2 equation, we write negative r1 theta, negative because shortened, r1 theta, this is displacement of pulley 1. For in case of spring 3, it will be extended, so we write positive r1 theta, and there will be no effect on spring 1, so we don't write anything on this spring equation. Now let's consider our second case where pulley 1 stays still and pulley 2 is moving at an angle theta 2. So the displacement it will have is r2 theta 2. Now what will affect these to the spring? Let's consider K1. K1 will extend, so that's why we write positive because it extends, and the amount of displacement which is r2 theta 2. For spring 3 it will be shortened, so we write negative R2 theta 2 for spring 2 it will not have any effect because this pulley is not moving. So that's our equation for spring 1, spring 2 and spring 3. In step 4 we want to obtain equation of motion. So for linear displacement the equation should look like this in case of free vibration. So A times acceleration plus B times velocity plus C times displacement equals 0. Right hand side 0 because this is free vibration. Same for angular displacement, just we use theta instead of x or y. For forced vibration, on right hand side we will have Ft, which is a force as a function of time most of the cases. In next step, which is a linearized equation of motion, what we need to do, we need to consider a static equilibrium condition of the system, which is most of the cases mentioned in the problem. So we use that static equilibrium condition and impose that condition on the equation of motion, and we should get static deflection of the springs. Once we get static deflection of the springs, we want to replace this value into the equation, and we should get this kind of form for free vibration and this kind of form as forced vibration. Now this is a matrix equation form where M being the mass matrix, and because this is a 2 degree of freedom, that's why we get 2 by 2 matrix for mass, and we also get K, which is a stiffness matrix, and we get 2 by 2 matrix because again this is a 2 degree of freedom. In case of force vibration, we'll also have force vector, which is have 2 elements because 2 degree of freedom, F01 and F02. So the first element of force vector, which is F01, you get it from first equation, and F02 you get it from second equation. You must notice that in this matrix equation we don't have velocity coefficient, which is a damper matrix, because in this unit we are using simple 2 degree of freedom equations, so we actually don't consider damper to this system. If there is a damper in the system, then this matrix equation should have if there is a damper component in the system, then we should have another part in this equation which contains damping matrix multiplied by the velocity. So we always get this form of equation for free vibration, neglecting damping. Once we get this free vibration matrix equation, the solution for this matrix equation is like this, where omega n1 and omega n2 are natural frequencies for 2 degree of freedom. Because this is 2 degree of freedom, so we get 2 natural frequencies. This one is called chi. Chi1 and chi2 are mode shapes, which can be expressed like this way. This is a vector, and it has a 2 component. First one is always 1. Just mode shapes represents how the system shape represent the shape of the vibration at each natural frequency. And this is a vector, so it can be expressed like this, where the first element will be always 1 and the second element will be a ratio. This ratio actually tell you how the system vibrates. Let's see how this x2 and x1 represents through the diagram. By the way, this x1 and x2 are the amplitude of motion. We'll have a diagram which will clear you a lot. Okay, so if we want to understand x1 x2 by x1 ratio that we already saw from chi1, let's consider that this mass m1 is moving left and right direction. So we consider this is x1 is the amplitude of the motion for mass 1, and if mass 2 is also moving, so this is the amplitude for mass 2, which is denoted by capital X2. So we can write their ratio as chi1, and here A1, A2 is the amplitudes, and phi1 and phi2 are phase. These are constants, and we can find them by imposing initial conditions. Alright, so now we want to find natural frequency of the 2 degree of freedom system, and to get the natural frequency we need to find determinant of this matrix, which is k minus omega n square times m equals 0, which means we take the determinant of this matrix as null, and that gives us the natural frequency. Once we get this determinant, the expression we get as quadratic algebraic equation. So you want to find the quadratic algebraic equation solution, and that's how we find natural frequency. In case of finding mode shape, we need to consider these matrix, which is k minus omega n squared times m, and x, where x, again, we showed already how to find amplitude of motion x1 and x2. So you multiply these two matrices and you get two equations. You just choose one, and from that one equation you get chi1 and chi2 respective of omega n1 and omega n2. For force vibration, we get matrix equation as this form, where on the right hand side we have force vector. So the solution of this vector matrix equation is x equal xh plus xp, h being the homogeneous solution and theta b being the particular solution, as we already know from single degree of freedom for vibration analysis. So the solution consists of a homogeneous part and particular part, as we already knew that for homogeneous part it actually disappear after a while, which we can write as equivalent to 0. So that's why we are more interested about particular part or particular solution, which can be expressed like this, where xp is the amplitude of this particular solution, and we are now more interested about amplitude of this particular solution, which can be expressed like this, where we want to get x1p and x2p as inverse of this matrix. To get this equation, we need to use Cramer's. Replace first column of this matrix with the force vector, and for second amplitude we replace second column with the force matrix. So once we get two particular amplitude, we want to plot them against force frequency. This capital omega is represents force frequency. So, and we want to consider three cases. Case 1, when the force frequency is equal to 0. Second case, when force frequency is equal to the damped natural frequency, or you can even consider natural frequency. And the third case, where we consider force frequencies tends to infinity, which means we consider very big value. And considering these three conditions, we plotted these two graphs for x1p and x2p. You can see for x2p we get null point, where in between two natural frequencies we get x2p is 0. This is called null point, and at this point the numerator of x is 0. At null point, the numerator of x, it could be any one of the amplitude, will be 0, and we get this null point between two natural frequencies. That means two resonance. Alright, so from this video you were introduced how to find natural frequencies for 2 degree of system. You were also introduced how to draw the mode shapes of the system and how to represent force vibration response in time domain. Thanks for watching.